Hello everyone, my name is Andrea de Marcellis. I am a professor at the University of L'Aquila in Italy. The title of this talk is a novel light-to-frequency converter-based analog front-end for optical sensing applications. The next generation of the telemedical diagnostic and therapeutic implantable, portable and wearable devices for effective and high-quality personalized healthcare requires suitable electronic analog front-end circuits that should guarantee low voltage, low power characteristics, high and variable gain, high detection sensitivity and resolution, good noise immunity, reduced number of electronic components, high integrability in standard CMOS technologies. For biomedical applications, wired and wireless dry electrodes are used in different systems including electroencephalogram, electrocardiogram, electromyography, and photoprismography. Among the dry electrodes, optical electrodes, named optrodes, have found extensive use in photoprismography, transcutaneous blood monitoring, and neural interfaces. Optrodes must be combined with suitable readout circuits to measure body signals. Generally, the proposed solutions are based on transimpedance amplifiers as the first conditioning circuit for the signal produced by the photodiode that is the light sensing device of optrodes. Alternative approaches for a direct light-to-signal conversion are circuits performing light-to-analog output signals, light-to-digital output signals, light-to-impedance outputs, light-to-frequency output signals. In this sense, here we propose a new oscillating circuit converting variations of the internal junction capacitance of a silicon photodiode directly proportional to the light intensity impinging of the photodiode sensitive area into a frequency modulation of a square wave. The designed analog front-end circuit operates a light-to-frequency conversion providing a quasi-digital output directly measurable by a frequency meter, so avoiding the use of transimpedance amplifiers or analog-to-digital converters. The circuit solution that we are proposing has been developed in current mode approach employing second-generation current conveyors as basic analog building blocks. The proposed solution has been implemented on a prototype board with commercial off-the-shelf components so to validate the idea and demonstrate the circuit capabilities in real-time detection of light intensity variations of a laser in steady state and pulsed operating conditions. The achieved results prove the suitability of the proposed circuit for CMOS integrated low voltage, low power, portable, wearable, implantable optical sensing systems with very good values of detection sensitivity and resolution. In this slide, we report the block scheme of the proposed analog front-end circuit. As introduced before, it converts the internal junction capacitance of a photodiode into a frequency-modulated square wave output signal Vout. As shown in this figure, it is composed by two main blocks: a derivator, where is connected a photodiode, followed by an hysteresis comparator. The two blocks are decoupled by a passive derivator so to eliminate any possible DC offset at the output of the derivator provided by the photocurrent generated by the photodiode. Its main characteristics are low voltage and low power operations, offset regulation and compensation, wide input current range, robustness to supply voltage and temperature drifts. More in detail, the oscillation frequency of the output signal Vout depends on the value of the internal junction capacitance of a photodiode that, in series to the resistor R1, implements a derivative cell. The value of the internal junction capacitance is directly proportional to the light power impinging on the photodiode sensitive area. So, any variations of the light intensity on the photodiode provides changes of the internal junction capacitance that, in turn, allow a frequency modulation of the square wave signal Vout. Here we report the approximated equation of the oscillation frequency of the output signal as a function of the internal junction capacitance of the photodiode and the other main circuit parameters, showing a nonlinear relationship. The circuit has been designed and simulated in PSpice environment, and then has been implemented with discrete components on a laboratory prototype board, as you can see in this figure, by employing AD844 by analog devices employed as second-generation current conveyors. Moreover, in this slide, we are reporting also the main settings and parameters of the circuit. A preliminary validation and an electro-optical characterization of the circuit have been performed by replacing the photodiode with high-precision, high-accuracy commercial capacitors emulating the internal junction capacitance of the photodiode. In this sense, the output frequency as a function of the capacitance ranging from 47 picofarad to 465 picofarad is in a good agreement with the theoretical behavior as reported in this figure, where the theoretical values are compared with the measurements. Moreover, by employing the optical setup here reported, other measurements have been performed related to the output frequency of the circuit as a function of the light power of a CW laser illuminating a commercial photodiode. In this regard, we have a linear response in a reduced variation range of the frequency with a very high detection resolution and sensitivity and low noise level. After the characterization of the system, a new optical setup has been implemented as reported here that can be used for optical sensing application. In particular, in this case, an electro-optical system has been implemented so that starting from a CW laser, it's possible to generate laser pulses impinging on the silicon photodiode. So in this case, we are generating pulsed current through the photodiode employed in this scheme. In this slide, we are reporting the results achieved by using the optical setup. In particular, we show the circuit response to laser pulses with exponential decay time, considering a laser pulse peak power equal to 8 microwatt and a pulse repetition period equal to 10 milliseconds. More in detail, here we are reporting a figure taken from the oscilloscope showing the square wave output signal with different frequencies as a function of the optical pulses having an exponential decay time equal to 4.1 milliseconds. From the raw data taken from the instruments, we calculated the output frequency of the circuit as a function of the time and extracted the related exponential decay time that is equal to 4.08 milliseconds. As you can see, the achieved result is in a very good agreement with the setup values. In conclusion, we reported on a novel current mode analog front-end circuit that performs a light-to-frequency conversion by measuring variations of the light intensity through a frequency modulation of a generated square wave voltage, so achieving a quasi-digital output. More in detail, the solution converts the internal junction capacitance of a silicon photodiode as a function of the impinging light intensity into an oscillating voltage signal, so avoiding the use of transimpedance amplifiers and analog to digital converters, and resulting suitable for portable, wearable, implantable devices and systems in biomedical and environmental applications. The proposed circuit characterized experimentally by employing commercial off-the-shelf components, shows capabilities of real-time measurements of steady state and pulsed light intensity variations. In particular, measurement results have demonstrated that the circuit is capable to achieve detection sensitivity equal to 5.32 kHz per microwatt and a detection resolution equal to 8 nanowatt. Thank you for your attention.